Hi guys! So today we're going to be talking about stereoisomers and chirality. Stereoisomers are important to know for organic chemistry because it gives us a lot of information about the different properties of organic molecules as well as information about the structure and optical activities and such. So today we're going to be talking about what kinds of isomers exist and some important terms to know for stereoisomerism in order to understand how their structures and properties work. So we're going to start by reviewing the different types of isomers that you should know. The first type is a constitutional or structural isomer, and these differ in their connectivities. And as you remember from perhaps an earlier chemistry course, isomers have the same chemical formula, but they differ in their atomic arrangement. So in the case of constitutional isomers, such as the example right here, we have the same number of hydrogens, the same number of carbons, and the same number of oxygens. However, the oxygen and hydrogen atoms are connected at different locations on the molecule. So for instance, this one's connected at the third carbon as opposed to the second carbon. And then the next type of isomer is a conformational or rotational isomer. And these differ in their rotations around a sigma bond. So a really common example of this is cyclohexane. You'll see that there are two conformations called the chair and the boat conformation. And it's really helpful to actually have a model kit or some 3D example of how cyclohexane looks like, so you can see how this conformation actually happens in a visually understandable way. But for our purposes today, we're going to try to envision this. So we have a chair conformation here, and if you imagine flipping the section upward, you'll see that it kind of rotates around. And these carbons that I'm marking here are the same ones that correspond onto this one. So these are the same carbons, and you'll see that this whole part kind of flipped upward, and there's rotation around the sigma bonds there. And that's how we get these two conformations here. And the last type of isomer that's important to know is a configurational isomer, and these differ in the spatial arrangement of atoms. And so these really don't fall into the category of constitutional isomers. They don't really fall into conformational isomers necessarily either, in the sense that they do have the same connectivities, and they don't experience bond rotation. However, the spatial arrangements are different. So if we look at these molecules down here, we'll see that the methyl groups are all connected at the same places. However, one is coming out of the page towards you, as indicated by this wedge figure here. And then one of the methyl groups is actually going into the page here, as indicated by the dashed lines. And so these methyls are all attached in the same places, but they're oriented differently in space. And that's what configurational isomers are about. All right, so now we're going to go over the different types of configurational isomers that are good to know. The first is called an enantiomer, and these are non-superimposable mirror images. So if you were to take this molecule here and try to slide it over or rotate it around and basically try to put it on top of its mirror image, you would find that they would not be able to be overlaid or overlined. And a good way to see this is to use model kits, so that way you can see how each of the attachments don't really overlap or align with their corresponding mirror images. And a good example that people often talk about when they talk about non-superimposable mirror images is you think about your hands, for example. So if you were to take your both of your hands and put them palms facing upward and try to overlap them, you would find that they're not able to be superimposed. So that's a good way to kind of think of it and help you remember what this means and what it looks like. Now, enantiomers have the same physical properties except for their rotation of plane polarized light. So I'm going to abbreviate plane polarized light with PLL here. And what that means is that, for example, you might have one of the mirror images rotating light in a clockwise direction, which is indicated with a plus sign, and this represents dextrorotatory rotation of light. And then you would find that its enantiomer, its mirror image, would rotate plane polarized light in a counterclockwise direction, which is indicated with this minus sign here, and that is stands for lever rotatory. And so you might see these pluses and minuses in a lot of organic molecules when it's being named, and that just refers to its optical activity. And then the other type we should know is called diastereomers, and diastereomers are not enantiomers, so they differ in the sense that you'll notice that one of the attachments, at least, is oriented differently in space. And I'm going to revisit this slide in a later video, but just to briefly go over it here, you'll notice that out of all of the attachments coming out of the cyclohexane ring here, we have this OH going inward here and this OH coming outward, whereas the other two attachments are the same. And so that's kind of one difference you can look for when you're looking at diastereomers versus enantiomers. And diastereomers actually have different physical properties most of the time, and you'll find that this is a very useful thing to have, especially when it comes to separating them, separating enantiomers in future experiments. And we'll talk about that a little bit later with a different video. So let's go over some important terms to know. The first is, if we were to take a look at this molecule again, we see that this is a very important molecule. This is called a stereocenter, which is a central atom with 3 or more different attachments. But in organic chemistry, you'll tend to see that most of the time when we're referring to a stereocenter, we're actually referring to a carbon. So it could be a carbon with 4 different attachments. So you might hear something like a tetrahedral carbon or a chiral carbon, and that's kind of what this means here. You have a carbon with 4 different things attached to it. But just know that a stereocenter is not necessarily always a carbon. The second important term to know is chiral, and this means that it's not superimposable on its mirror image. So again, we have these enantiomers here, and this molecule cannot be superimposed onto this one. So let's take a look at these example molecules here and decide, first of all, whether or not they are chiral. So the first thing we should look for is a chiral carbon or some kind of stereocenter. So here we're going to identify our stereocenter as this carbon here. Let's take a look at its attachments now and see whether or not the attachments are different. So we see here, I can tell that these 2 attachments are actually the same. So we're going to go with achiral here. Looking at this second choice, it looks like we have this as one of our stereocenters and this also as one of our stereocenters. So it's good to kind of remember, don't forget that there's some hydrogens attached here as well. And these can get kind of tricky with some types of ring structures, but it's important to kind of be careful with that and make sure you don't see molecules or attachments that are actually the same. So this would actually not be a chiral carbon here because these 2 methyl groups are the same. So in this case, we do have a chiral molecule. Let's take a look at this one. So here we have a chiral carbon. There's a hydrogen coming out of that right there. And we're going to go with it being chiral since there are 4 different things attached to the stereocenter there. And lastly, we have this molecule here, and we can tell pretty similarly and right away that these hydrogens are the same attachment to the carbon on this stereocenter. So we're going to go with an achiral molecule here. So a good rule to know for stereocenters to keep in mind is there's a rule where if you have a certain number of stereocenters, n, then that means you can have 2 to the n stereoisomers. So let's take this for example. We have 1 stereocenter here and 1 stereocenter here. And this means that we can have 2 to the second equals 4 stereoisomers that are possible. And I'm not going to draw them all out here, but just know that if you'd like, you can test it for yourself and draw out the molecules with the different spatial arrangements. Next, we're going to look at this molecule, this cholic acid molecule, and identify the number of stereocenters to figure out how many stereoisomers are possible. So we're going to circle them here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 stereocenters there. So 2 to the 11th is 2048. So we're going to have technically 2048 possible stereoisomers that can be drawn. So this is a good rule to keep in mind when you're counting up how many chiral carbons you can find. However, this rule, of course, is not foolproof. So let's take a look at this molecule here. And what you'll notice about this molecule is that it has this internal plane of symmetry. So you see that you might notice right away that there's possibly 2 stereocenters here. However, because these can be in a way superimposable on each other, this 2 to the n rule does not apply. And the reason for this is because this is a special type of molecule called a mesocompound. And mesocompounds are actually achiral molecules. However, they do have stereocenters, but they also have this internal mirror plane that allows them to be very symmetrical and also superimposable on their mirror images. So looking at this mesocompound again, you'll see these are stereocenters. However, the 2 to the n rule does not apply. And however, if we were to look at this molecule, if we were to draw this internal mirror plane here, we see that these are actually not reflections of each other. So this molecule here is still a chiral compound. So it does not fall into that compound of meso compounds. So just be careful when you're looking at these molecules, just because they have the same attachments on either side of the internal mirror plane of symmetry does not necessarily mean that it is a mesocompound. You just have to make sure that the arrangements in space are also the same across the different types of atoms that are attached. So that's basically a good rundown of stereoisomers, and thanks for listening, everyone.